processes of cooling water are among the oldest known. Some of these processes are slow, while others are comparatively fast. Either way, all of them involve the exposure of water surface to air in varying degrees. An example of which is what we call cooling towers. In this presentation, we are going to learn a few key concepts such as humidification, evaporative cooling, cooling towers, mechanical and natural draft towers, Merkel and Chebyshev's equations, sizing and horsepower charts, and fogging. Also, we are going to discuss the principles, types and parts, equations, sample calculations, and applications and ecological implications of our cooling towers.
Before anything else, let us first discuss the concept of humidification. Humidification is a process wherein the amount of water vapor present in the gas stream is increased by passing the stream over a liquid which then evaporates into the gas stream. It involves simultaneous mass and heat transfer. It is usually used to control humidity or to cool and recover water by contacting it with air that only carries a small mass of water vapor. The mass of water vapor carried by the unit mass of dry air is known as the humidity or the moisture content of air. The goal of performing humidification is to remove the waste heat from the water so that it can be reused in heat exchangers in an industrial plant. It is done due to economical reasons which would allow minimization of expenditure. Humidification is carried out through humidification equipments which are dependent on the unit size, convenience of recovering gas or liquid phases, and the materials of construction used. One type of these equipments which is commonly used in larger cooling duties is a cooling tower. A cooling tower is a heat rejection device in which waste heat is extracted from the atmosphere or input air by cooling a stream of water to a lower temperature. It operates under the principle that the cooling potential of a wet surface is much better than a dry one, since the greater difference between the temperature of the cooling liquid and the temperature of the surrounding air yields a greater potential for evaporative cooling. The heat from the water stream, which is transferred to the air stream, raises the air's temperature and its relative humidity to 100% before being discharged to the atmosphere. The heat rejection is evaporative since a small portion of the water being cooled is evaporated into the moving air stream to provide significant cooling to the rest of that water stream. Water is sprayed above the top deck of the cooling tower and is allowed to trickle down as droplets through various decks to a bottom collection basin, causing large area of contact between the water droplets and the surrounding air. The main purpose of a cooling tower is to conserve cooling water by providing significantly lower water temperatures that allow the cooled water to be reused as many times as possible, achieving more cost-effective and energy-efficient operation of systems in need of cooling. The mechanism of heat transfer process in a cooling tower involves 80% of heat transfer due to vaporization of small amounts of water known as a latent heat transfer, and the remaining 20% of the heat transfer is made up of sensible heat transfer that is due to the temperature difference between water and air. The theoretical amount of heat which may be possibly removed per pound of air circulated in a cooling tower is dependent on the temperature and the moisture content of air. The humidity or moisture content of air is indicated by the wet bulb temperature, since it is the lowest temperature which is theoretical that the water may be cooled. The wet bulb temperature is only approached by the cold water temperature but is never reached by it, since it is hard to make all the water trickling down the cooling tower decks to come in contact with the fresh air. Also, there will be no latent heat transfer, since the vapor pressure of the water would be equal to the vapor pressure that it would have at wet bulb temperature. For these reasons, the difference between the actual temperature of the cooled water and the theoretical temperature it can be cooled is determined. This is known as the approach. Its magnitude is dependent on the tower design, which include the air-to-water contact time, amount of filled surface, and breakup of water into droplets. Approaches for cooling towers rarely reach 2.8 degrees Celsius or 5 degrees Fahrenheit.